we continue with the following theorem. So now we consider a norm space X. Then the closed unit ball is compact if and only if your norm space is finite dimensional. So if X is a finite dimensional, then we will see later that this follows immediately from the Heine-Borel theorem, stating that the norm space K to the N is finite dimensional. So the closed unit ball is compact. And here we call that the closed unit ball is the set of all elements in your vector space having a norm less than or equal to 1. Take note that this is a closed subset. Okay. In the case when X is infinite dimensional, this is closed and bounded, but not compact. So the Heine-Borel theorem is not valid in general, even for normed spaces, if the dimension of X is infinite. So we have here an example of a closed and bounded subset of your infinite dimensional norm space, wherein it is not compact. Of course, there's nothing usual with or special with having a center at 0, that is the 0 element of your vector space, and the radius 1. You can, in fact, prove this in the general closed balls. And just to give you an idea, of course, let's say we have a center X and a radius R, okay? And suppose that you have a covering of this, okay? So think, for instance, first think of an infinite covering. What you do is, okay, you do scaling and translation. So let us copy this one. And then we do scaling. We shrink the radius or expand in such a way that your radius will become 1. So now we have a radius 1, and the center is now in 0. So this is your center, and your radius now is equal to 1. So what you do is you scale and possibly translate if the center is not the origin. So again, if you have an open covering of this ball centered at X with radius R, you translate and scale that covering, and you will have a covering of the unit ball, closed unit ball, since let's say if you are in the finite dimensional case, then you can reduce the open cover by a finite subcover, and you go back, you take the inverse, okay? So if you contract, the inverse of that is expanding, and vice versa. And then you take the inverse of your translation. Since the cover here has been reduced, the translated and scaled covering of the unit ball will comprise a finite covering of the original ball, and vice versa. Okay. So if you have a covering of this, so if this is not compact, let's say think of the infinite dimensional case. If this is not compact, then there must be a covering that cannot be reduced to a finite subcover. Again, scaling and translating those open sets in the covering will give you an open cover of the unit ball having with no finite subcover. And that would imply that your space is also infinite dimensional. So again, as I said, there's nothing special in the center 0 and radius 1. This is also valid in the case of general closed balls by translation and scaling. So I will leave the technical details for you to write. So let us go to the proof of this theorem. And we need to prove two directions. Let's go first with the easy case. So suppose that you have a finite dimensional space. And to prove this, we need the following. To prove the compactness of the closed unit ball, we need the following lemma. So all norms in a finite dimensional space are equivalent. So if X, let's say, is a vector space, and the dimension of this is finite, and I have, let's say, two norms with subscript A and B. Then it is possible to find, or there exists a constant C1 and C2 such that the norm of X with respect to the first norm with subscript A is less than C2 times the norm of X with subscript B. So we don't, let us denote the norm by double bars. And in turn, this is greater than C1 times the norm of X and B. For all X in your finite dimensional vector space. Okay, so these are this is the first lemma in order to prove the compactness of the unit ball in a general finite dimensional vector space. Before proving this implication, let us first prove this lemma. Okay, so suppose that our dimension is n, and let us consider a basis for x, say e hat 1 to e hat n. We define a map J from Kn into X as follows. So it maps an n tuple of elements in Kn K here is the underlying field of your vector space. Let us define this to be the linear combination of your basis in X with coefficients in this n tuples in Kn. And this is clearly an element of X. Then, one thing for sure, J is bijective. Well, it is one-to-one due to the independence of your basis, and it is onto due to the fact that the basis spans your vector space. The function, okay, defined from Kn to R, given as follows. So you take the norm of the image. You can verify that this is indeed a norm on Kn. So I leave the details for you to check. Well, this follows from the fact that, well, you can also say that it is so your mapping J is linear. So it follows from the fact that you have a norm in X, okay, and J is bijective in linear. Okay, and from those properties, you can indeed verify that this is a norm on Kn. Therefore, J is an isometric isomorphism between your space Kn equipped with this norm and X with respect to this norm. Isometry is basically by this definition of your norm in Kn. So automatically, J would be isometric with respect to these norms in Kn and in X. It is an isomorphism, yes, because it is linear and bijective. Okay, so here, our idea is to, okay, consider an isometric isomorphism from X into Kn. Of course, to be an isometry, you need a distance, or in this case, you need a norm. So here we defined the norm via this map J. And let me give you the idea why it is sufficient to show that so now it is enough to show that any norm in Kn is equivalent to the Euclidean norm. And let us denote the Euclidean norm by a subscript 2. Well, the idea is the following. Let us consider two norms in X, differentiated by a subscript A and a subscript B. We can now define norms in Kn above. So to distinguish the norms, let us also denote it by a subscript. So in other words, if this is A, then this is also A. If this is B, then this is also B. So these two are isometric. In other words, a distance preserving. So the norms are equal with respect to the map J. Now, if we, let's say, establish that all norms in Kn are equivalent to the Euclidean norm. So if this is equivalent and this is also equivalent, then, well, you can check immediately that equivalence of norms is an equivalence classes. It's an equivalence relation, I should say. So it is transitive, therefore these two norms in Kn are equivalent. So therefore, showing that any norm in Kn is equivalent to the Euclidean norm implies that any two norms in Kn are equivalent due to the transitivity of equivalence between norms. So when you say iso, you can think of equality with respect to the mapping J. So if this norm is equal to this, and this is equal to that, and furthermore, this is equal to this, so one can show that this is, or these two are equivalent. So that's the main idea of why it is enough or it suffices to establish the equivalence of any norm in Kn with respect to the Euclidean norm. And let us show this one. So to start, let's say let us consider a norm on Kn. And let us denote by E1 to En the canonical basis of Kn. So these are vectors with one, let's say in the case of R to the N, vectors with component one in the ith entry and zero otherwise. Okay, so this means that I can write an n tuple nkn in the following way. According to the triangle inequality, and homogeneity of the norm, okay, this norm in particular, we have the following inequality. Okay, so the absolute value here refers to, on the right, refers to different things. So this is the norm, let's say in Kn. And for this one, this is either the absolute value or modulus, depending whether your field is the set of real numbers or the complex numbers. Okay. So do not be confused with this same notation. Well, in any case, these are real numbers. So applying the Cauchy-Schwarz inequality, you have the following. One to n ej squared 1/2. Now, if we define the second term as, let's say, C2, so let this to be C2. This is nothing but the Euclidean norm of X. So we have the following. Okay, so this is one inequality in order to prove the equivalence of this norm with respect to the Euclidean norm. To prove the reverse inequality, let us define C sub 1 to be the infimum of the norm of X where X has a Euclidean norm equal to 1. Since the norm is non-negative, this is non-negative as well. Now, let us see what if C1 is 0. Then there must be a sequence, let's say X sub K. Okay, and we denote it by a superscript to distinguish a subscript for the components. So there's a sequence such that this one tends to 0, and the Euclidean norms are all equal to 1. So we have here a bounded sequence. So if we apply the Bolzano-Weierstrass theorem, we can find a subsequence that is convergent. So by Bolzano-Weierstrass theorem, this bounded sequence has a convergent subsequence. So subsequence converges to X, and moreover, the limit is also in or has also a Euclidean norm 1. Okay. So to be precise, what do we mean by this convergence here? This means that the convergence is with respect to the Euclidean norm. Now, if we apply the, let's say, the inverse triangle inequality with respect to this norm, let's say xkj, this is the norm between the difference, but we know that, okay, according to this one, it's less than a C2 times xkj minus x, but now in the Euclidean norm. Okay, and this would be corrected, should be only convergence to 0. So this also converge to 0. Therefore, this one tends to 0, tends to the modulus of, or the norm of X, okay, by squeeze theorem. So that by uniqueness, okay, what do you mean by a uniqueness? Here we know that the whole sequence tends to 0. Here we have a subsequence that tends to the norm of X, okay? So if you have a convergent sequence, then any subsequence should be also convergent, and it must converge to the same limit. So that the norm of x is 0, hence x must be 0. And there's a problem here. This contradicts the fact that the Euclidean norm of x is 1. Okay, so this is not true. This means that we must have C1 to be positive. Now, with this, we can now compute as follows. For x, let's say, not equal to 0, we can write the norm of x as follows. So Euclidean norm of x divided by the Euclidean norm. So the assumption that x is not equal to 0 is provided here so that the denominator will not vanish. Now, applying the homogeneity of your norm, you have the following. But if you look at the Euclidean norm of this, again, homogeneity implies that this is equal to 1. So therefore, this has a Euclidean norm equal to 1. Since C1 is the infimum, therefore the second factor must be greater than C1. Times the Euclidean norm of x2. So writing that in this way, so C1 times the Euclidean norm is less than or equal to this given norm of x. So we can now conclude therefore our Euclidean norm is equivalent to the given norm. And this is due to this inequality here, and the reverse was already established before. And that ends the proof as we have discussed a while ago. In other words, any norm in Kn is equivalent to the Euclidean norm. Therefore, by transitivity, any norms in Kn are equivalent. And applying our isometric isomorphism, this would imply the equivalence of all norms in the finite dimensional vector space X. So going back to the proof of this theorem, okay. So assuming that X is finite dimensional, we wish to show that the closed unit ball is compact. So let us continue the proof there. Observe that using the notation of the proof in the lemma, here B1 is the ball and Kn with respect to the norm induced by the norm in X and the mapping J, the isometric mapping J. Take note that this is compact in Kn by the Heine-Borel theorem, and the fact that equivalent norms yield the same topology, metric topology to be precise. So if you have equivalent norms, then the induced metrics are also equivalent, and thus the metric topologies must be the same. Now, see, this B1 here is compact. Since J is continuous, in fact, it is Lipschitz continuous. Okay. The image of a compact set under a continuous map is again a compact. So this implies that the closed unit ball in X, this is a compact. And that's the end of the proof of the reverse implication. And with respect to the second one, we prove it by contraposition. In other words, suppose that the dimension of X is infinite. We will show that the closed unit ball is not compact. And again, we need a lemma to prove this. So let's start with a norm space Y to be a closed subspace of X not equal to X. Okay. For each parameter, let's say theta, between 0 to 1, it is possible to find an element x theta in X that lies on the boundary of the closed unit ball. In other words, it has a norm 1, and the distance of this x theta with respect to the closed subspace Y is greater than 1 minus theta. So to have, let's say, an intuition of what is or what's the content of the theorem, let's say we have our X to be R3 and Y to be the x-axis. So that would be R cross 0 cross 0. So if we take, let's say, a theta between 0 to 1, we would like to find a distance that is larger than 1 minus theta. So for instance, you can take, and of course we wanted the norm is equal to 1. So for instance, you can take the point here so that the distance of this line segment here is, let's say, 1 minus theta, or let's say greater than 1 minus theta. And that would be your x theta. So the distance in this case would be greater than 1 minus theta. It is in the unit circle on the xy plane. So as theta goes to 0, take note that you need to go, let's say, in this direction. So if you want a theta to be close to 0, that is 1 minus theta would be going to 1. Okay, then from the left, okay, from the left of 1. So you need to move this x theta here also in this direction. So passing to the limit, let's say if theta is equal to 0, you can pick at this point. Okay. Now, to prove this theorem, okay, let's start with the assumption that theta is less than 1, but positive. So 1 minus theta would be greater than 1. Since the denominator is less than 1, this fraction here must be greater than 1. It is possible to take an element, say z theta in x minus y, and y theta in your subspace, such that the distance between these two is less than this number greater than 1 times the distance of z theta to y. Okay, so you can find a y theta such that the distance between z theta and y theta is less than this product here. So here, take note that this quantity is larger than the distance itself because the factor is greater than 1. And this follows from the definition of distance, which is an infimum. And it is clear that we can take a z theta in x, which is not in y, due to our assumption that y is not equal to x. And since z theta is not in y and y theta is in y, the distance between these 2 points must be positive. They must be distinct. So there's no reason that z theta has a norm 1. What we can do is we can pick x theta to be this difference divided by the norm. So we normalize the difference, and obviously now this one has a norm equal to 1. And if we compute the distance between x theta and y, okay, so here you can pull out the scaling factor in the distance since y is a subspace. Again, since y is a subspace, we can translate then this is the same as the distance between z theta and y. And according to this, okay, if we divide this quantity both sides of this inequality and then put this on the other side, you end up with the following inequality. So this should be greater than 1 minus theta as the side. Okay. So again, according to this lemma, if you have a closed subspace not equal to x, you can find, given any theta, wherein the distance between a point having norm equal to 1 with y is greater than 1 minus theta. So going back to the proof, so assuming that x is infinite dimensional, so first let us pick a particular x1 and x. If I take theta to be 1/2 and y to be the linear span of x1, since x is infinite dimensional, this is of course not equal to x. And from here, we can find, let's say, an x2 with norm equal to 1. So in particular, it is in the closed unit ball, such that the distance between x2 and y so let us say it's y1, okay, is greater than 1/2. But of course, this is greater than, or I mean, this is less than the distance between x2 and any particular point in y1. So let us take x1. So going back to the figure, let's say, for instance, you take x1 to be your canonical basis, this point here. You need a distance greater than 1/2. So what if, let us take, let's say, x2 to be e2. And this would be your vector. So take note that the distance here is in fact equal to 1, so greater than 1. So next, you now have the xy plane. Now that you have the xy plane, we want a vector that has a distance with respect to the xy plane greater than 1/2. And we can take, let's say, the next point, let's say x sub 3, to be e sub 3. So that's the next step. So you do this inductively. So suppose x1 up to, let's say, xn has been chosen. We then take theta again to be 1/2 and yn to be the linear span of x1 up to xn. Since x is infinite dimensional, this must be different from x. So taking this theta in the previous lemma and this yn, we know that the distance between x n plus 1 for some xn plus 1 in the closed unit ball and yn is greater than 1/2. But again, this distance is less than or equal to the distance of xn plus 1 minus x for any x in your subspace yn. So in particular, let us take this one. For j, from 1 up to n, 2 up to n. Okay. Therefore, by construction, we have constructed a sequence where in x sub k minus x sub j, the norm is greater than 1/2 for every k greater than j. So if your indices are distinct, they are greater than 1/2 distance apart the terms of your sequence. So this means that your sequence xk, and by construction, this is a sequence in the closed unit ball, has no convergent subsequence. So therefore, this is not pre-compact, and hence it is not a compact. And this is the contrapositive or contraposition of this direction. So if your vector space is infinite dimensional, then the closed unit ball is not compact. Okay, and that's the idea of the proof. So you pick one vector, you take another vector that is this having a distance greater than 1/2 to the subspace is spanned by the previous vectors. So in the case of infinite dimensional spaces, you can, let's say, imagine, or loosely speaking, you don't you will not lose. Okay, you will always have a vector that will be chosen to which for which the distance with respect to the spanning set of the previous ones is still greater than 1/2. Kumbaga, hindi ka mawawalan ng vectors na kukunin. So this is an example of classical results in finite dimensional calculus, not holding in the infinite dimensional case. So although there are a lot of analogies, but one should be very careful that in general, it may not be possible to extend what we know in the calculus of finite dimensional vector spaces. So an example of this is that we have here a closed and bounded set, but not a compact set. So if you think, for instance, the little LP spaces, they're infinite dimensional. So the closed unit ball is not compact. In the next lecture, we will discuss compactness of the space of continuous functions defined on a compact metric space, namely the Artzela-Ascoli theorem.